Welcome to the Deep Dive, the show where we tackle your fantastic questions, digging deep into the research to really get to the bottom of things. And today, well, we've got a truly stellar question from K. Brad Barfield over at Ashley County now. It's one of those things I think a lot of you might have noticed driving around, but maybe never fully grasped the deep geology behind it. K. Brad wrote in saying, and I'll quote him here, "Still want to know why the coastal plain has gravel deposits and red clay and just that quick as it turns into the delta. No rocks or gravel and sandy loam and buckshot soils." And he added a bit more context, mentioning Billy Joe Harrison from Ashley County now, saying, "It's just always amazed by it. I was raised on Bayou Bartholomew at Yorktown, Lincoln County, the divider between delta and coastal plain. Just dirt, no rocks. Live on the edge of coastal plain now in gravel pits. Maybe we can help him figure out things." Okay, Brad, that question, especially that phrase, just that quick, really nails something super visible and, well, geologically profound right there in Arkansas.
Oh, absolutely. It's a fantastic observation, K-Brad, and we are definitely going to help you figure out the thing, as you put it. You've perfectly captured this puzzle. You've got the West Gulf coastal plain things, rolling hills, pines, those gravels, the distinct red clay. And then, like you said, just that quick, boom, you're in the Mississippi alluvial plain, what most folks just call the Arkansas Delta. Vast, flat, super fertile farmland, and crucially, no rocks on the surface, just those sandy loams and the famous buckshot clays. So our deep dive today, it's all about peeling back those layers of time. Hundreds of millions of years, actually. We need to understand why this boundary exists, what forces shape these two totally different worlds. We're talking ancient continents, even the last ice age. It's quite a story.
I'm ready. Let's start with really getting a handle on this great divide that K. Brad observes so well. Okay, so K. Brad, first off, you are absolutely right. What you're seeing isn't just some subtle change. It's a really striking, immediate contrast. Anybody who's observant, driving east through southern Arkansas, you've probably felt it. That moment, the rolling piney hills just suddenly stop, and then it's just this vast, flat agricultural landscape stretching out forever. It really does feel like you've crossed into a different state almost, and like you said, just that quick, often in just a few miles.
Precisely. And you nailed the key features, the coastal plain. Reddish clays, you see those gravel deposits, maybe even gravel pits, like you mentioned, being near. Then bam, the delta. Deep, dark, fertile soils. You get sandy loams, maybe near old riverways, and then those heavy buckshot clays further out. And like you pointed out, a total lack of surface rock or gravel. It's just different. It's what geologists call a physiographic transition, a fundamental shift.
Now, the term fall line came up in the research.
Yeah.
When I hear fall line, I kind of picture waterfalls, a big drop. Is that what's happening here?
That's a great point. The classic fall line, yeah, that often marks where rivers drop from harder mountain rocks onto softer coastal plains, creating rapids, waterfalls. We see that elsewhere. But here, between the Gulf coastal plain and the Mississippi alluvial plain, it's a fall line in a slightly broader sense. It's less about a dramatic cliff and more about the boundary between two fundamentally different geological provinces. They were formed by totally different processes over completely different timescales. So it's still a major geological boundary, just maybe less vertical.
Ah, okay. So it's not necessarily a steep drop-off everywhere, but it's where two completely different geological stories meet head-on.
Exactly. You're looking at two landscapes forged by fundamentally different forces. Think of the Gulf coastal plain as the older, more stable upland. Its story is millions and millions of years of slow weathering, slow erosion, transforming ancient sediments that were laid down long ago. The Mississippi alluvial plain, the delta, that's the opposite. It's geologically young, it's dynamic, it's still being actively built by rivers dropping sediment right now. Well, almost.
Wow.
So that quick transition, K-Brad noticed, that's literally the visible edge where this super slow, long-term weathering world meets a rapid, ongoing depositional world. Deep time meets recent history.
A temporal and process-driven chasm. That really paints a picture. It's like a boundary in time, not just space.
That's a perfect way to think about it. It's not just a line on the map. It's this profound difference in age and process. The surface of the coastal plain, the actual stuff you walk on, its parent materials, the sands, clays, gravels, deep down they could be 50, even 100 million years old. And the soils on top have been developing for millions of years.
Okay, wow.
The delta surface, the stuff crops grow in, that was mostly laid down in the last, say, 10,000 to 12,000 years. Since the last glaciers melted.
Millions of years versus thousands. Okay, K. Brad's just that quick. Suddenly feels even more dramatic. The timescales are just staggering.
They really are. And there's a deeper reason why this boundary is where it is. It's controlled by a massive geological structure underneath everything called Mississippi embayment. Imagine a huge, shallow, south-plunging trough or dip in the Earth's crust, like a giant tilted bathtub extending way north from the Gulf. Back in the Cretaceous and Tertiary periods, this whole area, this embayment, was actually an arm of the Gulf of Mexico. It reached almost up to southern Illinois.
An ocean bay reaching up to Illinois. That's hard to picture.
It is. Now, the Gulf coastal plain that we see today, that represents the older tilted layers of sediment exposed along the western edge, the western flank of this ancient trough. So you're kind of standing on the sloping bank of this old, now sediment-filled bay. And the Mississippi alluvial plain, the delta, that's the recent stuff. The flat-lying sediment that has filled up the middle, the central axis of that trough. It's the modern flat floor of that ancient bay. So the boundary isn't just random. It follows the edge of this huge underlying structure. That's why it's so sharp.
But that analogy is brilliant. Standing on the sloped bank, looking down onto the flat floor, that really helps visualize it, like seeing geology in 3D.
Exactly. That deep structure dictates where the quick transition happens.
So for Kay Brad, who grew up right there on Bayou Bartholomew, and for anyone else traveling, can we trace this line? Where exactly is it in Arkansas?
Absolutely. It's pretty well defined by major rivers. If you look at a map of Arkansas, the eastern edge of the West Gulf coastal plain roughly follows the Arkansas River. It runs from around Little Rock southeast down towards Pine Bluff. Then from Pine Bluff, the boundary basically hooks south and follows Bayou Bartholomew all the way down to the Louisiana border. These rivers aren't just incidental, they mark that geological separation. Older, weathered uplands to the west, young river deposits to the east. So, Kay Brad, your childhood home was literally right on this incredible geological dividing line.
That's amazing. It's literally where the story of an ancient seafloor meets the story of a modern river delta. Okay, I get the big picture now. Let's dig into that ancient seafloor side, the coastal plains gravels and red clay. All right, let's rewind the clock. Way back. We're talking Cretaceous, Tertiary periods, 135 to 50 million years ago. Southern Arkansas underwater. What was that like?
It was a completely different world. For huge stretches of that time, yeah, southern Arkansas was submerged beneath a warm, shallow Gulf of Mexico. But it wasn't static. Sea levels went up, they went down repeatedly over millions of years. The coastline moved back and forth. So you had all these different environments being created and buried. Shallow ocean shelves, coastal lagoons, big river deltas, dumping sediment into the sea. And as these shifted, they laid down these incredibly thick layers of different stuff. Sand, clay, marl. That's kind of a limey mud limestone itself. And critically, for Kay Brad's question, layers of gravel. These became the parent materials, the source rocks for the soils we see today. It's a landscape built from ancient sea bottom and shorelines.
So we're not just guessing. There are actual rock layers, geological formations that geologists point to as the source of this gravel and the material that became the red clay.
Oh, definitely. The rock record is quite clear. For example, back in the early Cretaceous, there's something called the Trinity Group. It's a mix of sandstone, gravel, clay, limestone. And the bottom part of it, the basal member, is called the pike gravel. And this isn't trivial. It can be up to 100 feet thick.
100 feet of gravel, wow.
Yeah. It's a major source for the gravel beds you see across the region, like in those pits Kay Brad mentioned. Ancient river channels, coastal deposits, basically. Then fast forward a bit to the Paleocene-Eocene Wilcox Group, maybe 56 to 34 million years ago. Another huge stack of sediments, maybe 1,800 feet thick in places. This stuff was laid down more by rivers and deltas near the coast. Lots of sand, silt, clay, even lignite, that's like a low-grade coal from ancient swamps. But crucially for the red clay story, the Wilcox and similar formations have lots of ironstone concretions and other minerals containing iron. Little iron-rich nodules and bits scattered through it.
So that's the iron-rich parent material we need for the red clay. Okay, that makes sense.
Yeah.
So let's talk about that iconic red clay. It's not just dumped there like the gravel.
Right.
It's different.
Exactly right. That deep red clay isn't a sediment layer that was deposited, it's the result of intense chemical weathering of the original sediments. It's the profoundly altered remnant. The process responsible is called lateritization. Think of it as a long, slow, natural chemical transformation.
Lateritization. Sounds intense. What did it take? What were the magic ingredients, the conditions needed to turn regular old sediments into this deep red stuff?
It's a very specific recipe, and it needed millions of years. First, like we just said, you need iron-rich parent material. Check. The Wilcox and others provided that. Second, you need a specific climate, not like today. Think hot, humid, tropical, or subtropical, but crucially, with really distinct wet and dry seasons, alternating downpours and dry
How do
spells.
we know it was like that?
Well, those lignite beds in the Wilcox, that's fossilized swamp vegetation. That tells us it was warm and wet enough for lush swamps to thrive for long periods. It's fossil evidence for that ancient climate. And the third ingredient, time. Lots and lots of time. Lateritization is incredibly slow. You needed millions of years where the landscape was relatively stable, low-lying, not eroding too fast. This allowed the weathering processes to penetrate deep into the ground without the soil just washing away. Stability was key.
Okay, so iron, a hot, wet, dry climate, and millions of years of just sitting there cooking. Incredible. How does the chemistry actually work? How do you get red from, say, gray or brown sediments?
It's basically a process of subtraction and concentration. During those intense rainy seasons, rainwater soaked into the ground, it picks up CO2, becomes slightly acidic, like weak soda water carbonic acid. This weak acid slowly dissolves the more soluble minerals in the parent rock. Things like silica, calcium, magnesium, potassium, they get dissolved and leached away by the water moving down through the soil.
Stuff gets washed out.
Exactly. It's like making coffee. The water dissolves the good stuff and leaves the grounds behind. Here, the water carries away the soluble minerals. What gets left behind is a concentrated residue of the least soluble stuff, and that happens to be oxides of iron, and aluminum geologists call them sesquioxides. Then, during the alternating dry seasons, this iron-rich residue near the surface gets exposed to oxygen. It oxidizes, it basically rusts. This forms minerals like hematite, that's really red, and goethite, more yellowish-brown. These iron oxides are potent pigments. They stain the whole soil mass, those deep red and rusty yellow colors. It's continental scale rusting over millions of years.
So the red clay isn't something added, it's the concentrated leftovers after everything else dissolved and washed away. It really is like the ghost of the original rock.
That's a perfect description. It's a residual soil, the gravel and sand. That's the tough quartz stuff that didn't dissolve. The red clay. That's the ghost of the less stable minerals, concentrated and rusted. And in some places in Arkansas, this process went even further. Where the parent rock was really rich in aluminum, extreme lateritization formed bauxite aluminum ore. Same process, just concentrated aluminum instead of iron.
Wow.
So when you're walking on that red clay in the coastal plain, you're walking on a paleosol, an ancient fossil soil formed under a totally different climate millions of years ago.
A fossil landscape. That's mind-blowing.
Yeah.
But you mentioned another source of gravel, too, besides the really deep bedrock. Something about terraces.
Yeah, there's another layer to the gravel story. You also find gravel in what are called Quaternary Age terrace deposits. Picture these as old, abandoned floodplains. Rivers flowed across this area millions of years ago at higher elevations than they do today. They left behind sand and gravel on their floodplains. Then maybe the land slowly uplifted or the rivers cut down deeper, so those old floodplains got left high and dry, forming these flat, elevated benches or steps on the landscape. Terraces.
Okay, like fossil riverbeds up on hillsides.
Kind of, yeah. And these terrace gravels represent a much older phase of river activity than the rivers building the delta today. So those gravel pits K-Brad sees, they could be digging into the ancient pike gravel bedrock or these old high-level river terrace deposits. Both tell a story of an ancient, stable landscape.
So the coastal plain is this ancient world, old seas, intense chemistry, fossil soils, ancient rivers, deep-time stuff. Okay, let's cross that sharp line now into the delta. Okay, so we leave the ancient, weathered coastal plain behind. We step across that abrupt line into the delta, the Mississippi alluvial plain. You called it a landscape of profound youth. Just how young are we talking? And what built this world?
The contrast is just night and day, isn't it? While the coastal plains roots go back tens, even over 100 million years, the actual surface of the delta, the farmland, the ground you see, is mostly a product of the last 12,000 years or so, the Holocene epoch. Now, the foundation beneath it, the deeper stuff, was laid down during the whole Quaternary period, the last 2.6 million years. But the skin is super young, geologically speaking. Fundamentally, the MAP is the surface of a deep alluvial basin. It's a trough filled with an absolutely massive amount of unconsolidated sediment, loose sand, silt, clay, some gravel mixed in deep down, all of it brought here and dumped by the Mississippi River and its tributaries.
And that huge amount of sediment directly answers K-Brad's point about no rocks or gravel on the delta surface, right? Just buried everything.
Exactly. This alluvial fill is incredibly thick. On average, it's over 100 feet deep across the delta. In some spots, it can be 200 feet deep. With that much recent, loose sediment piled on top, Any actual bedrock, whether it's the edge of the coastal plain formations or even older stuff, is buried way, way down. You'd have to drill a very long way to hit anything solid. It completely blankets the older landscape.
Okay, 100, 200 feet. That's a lot of dirt. What was powerful enough to dump that much material? What was the engine driving this?
The engine was the climate roller coaster of the Pleistocene epoch, the Ice Ages. The repeated cycles of massive continental glaciers advancing and retreating across North America. That was the key. Think of it in two phases tied to the ice. Phase 1, glacial maximums. When the ice sheets were huge, they locked up enormous amounts of the world's water. This caused global sea levels to drop dramatically, maybe 400 feet lower than today.
400 feet lower. Wow.
Yeah. And dropping the ocean level that much drastically steepened the Mississippi River's slope, its gradient. It turned the river into a superpower erosive force. It basically became a giant geological chisel, carving a deep, wide valley trench into the older, softer coastal plain sediments. It excavated the basin.
And Crowley's Ridge is the evidence, the bit that didn't get carved away.
Precisely. Crowley's Ridge, that distinct upland running through the delta. It's not mountains, it's an erosional remnant. An island of older coastal plain stuff left standing high as the ancestral Mississippi and Ohio rivers carved massive valleys on either side of it during those low sea level times. It's proof of how much erosion happened.
Okay, so the glaciers caused the river to dig a huge ditch. What about filling it back up?
That's phase 2, interglacial periods. When the climate warmed and those massive ice sheets melted, they released just unbelievable amounts of meltwater. And this water wasn't clear. It was choked with sediment, all the rock the glaciers had ground up as they scraped across the continent. Gravel, sand, silt, clay, a huge load. At the same time, sea levels were rising again because all that meltwater was flowing back into the oceans. This rising sea level reduced the river's gradient, slowed it down, so the river lost energy. It couldn't carry that massive sediment load anymore. It started dropping it, dumping it in the valley it had just carved. It backfilled the trench.
And this happened over and over. Dig the ditch, fill the ditch.
Exactly. This cycle of deep valley cutting during glacial maximums, followed by massive valley filling during interglacial melts, repeated multiple times over the Pleistocene. That's what built up that incredibly thick stack of unconsolidated river deposits that is the delta's foundation.
So wait, if the sediment came from glaciers grinding up the continent, the soil in the delta isn't even originally from Arkansas, it's imported.
That's exactly right. And it's one of the coolest things about the Delta. Its soils are not native in the way the coastal plains residual clays are. They are imported materials. They're made of bits of rock scraped off a huge drainage basin covering like 40% of the continental U.S. Think of the glaciers as giant rock grinders, pulverizing everything from quartzite in South Dakota to granite in Missouri, limestone from Iowa, you name it. And the Mississippi River acted like a giant conveyor belt, collecting all that ground-up rock flour and debris and hauling it south, depositing it right here in Arkansas, building the delta layer by layer.
A continental conveyor belt,
Yeah.
delivering ground-up mountains. I love that. Okay, so this massive load of mixed sediment gets dumped. How does that turn into the specific soils K-Brad mentioned, the sandy loams and the buckshot clays? How does the river sort it all out?
That's the beautiful physics of river deposition or alluviation. A flooding river is basically a giant sorting machine. It separates sediment based on particle size and how fast the water is moving. Let's think about the sandy loams first. Near the main river channel, during a flood, the water is fastest, most energetic, most turbulent. When that fast water spills over the banks onto the floodplain, its velocity drops suddenly, right? It slows down fast. That sudden loss of energy makes the river drop its heaviest cargo immediately. That's the sand and the coarser silt particles. Over many, many floods, this coarser stuff piles up right along the edges of the channel, building slightly raised ridges. We call these natural levees. So these natural levees are made of coarser, better drained soil, sandy loams. Historically, these were the prime spots, the slightly higher ground for farming and building. The cottonlands.
Right, even a few feet of elevation makes a huge difference in a flat landscape, especially for drainage. That makes perfect sense. So that explains the sandy bits. What about the clays?
Okay, now imagine the floodwater spreading further out, way out into the low-lying areas, the back swamps, maybe old abandoned channels. Out there, the water is moving very slowly, or it might even become stagnant, just sitting there. It's a super low-energy environment. Here, finally, the very finest, lightest particles, the tiny clay platelets that can stay suspended in water for ages, finally get a chance to settle out. Slowly, gently. Over time, this slow settling builds up thick layers of heavy, dense, often poorly drained clay soils in these broad, flat areas away from the main channels.
And these are the buckshot clays Kay Brad mentioned. Why that name? Buckshot. It's so specific.
It is, and it's brilliantly descriptive. Scientifically, we call these soils vertisols. Vertisols are famous for having lots of smectite clays. Smectite clays do something dramatic. They shrink when they dry and swell when they get wet. A lot. So when these clay soils get really wet, they soak up water, swell, and become this incredibly sticky, dense goo. Farmers call it gumbo. Try driving a tractor through that.
Right, I've heard that term. Sticky gumbo mud.
Then, when these soils dry out, they lose water and shrink dramatically. This causes deep, wide cracks to form, sometimes going down several feet. Now, here's the cool part. The very top layer of soil dries out, maybe crumbles a bit. Then, bits of that dry, crumbly surface soil fall down into those deep cracks. The next time it rains heavily, the soil swells up again, closing the cracks. This churning action mixes the surface stuff down into the subsoil. This constant shrinking, cracking, swelling, and self-mixing, plus the way the surface breaks apart as it dries, creates these small, hard, roundish pellets or aggregates on the surface. And sometime, thought they looked just like shotgun buckshot scattered on the ground.
Wow. So the name comes directly from the soil's physical behavior, that constant cracking and crumbling.
Exactly. So the pattern you see in the delta sandy ridges near old channels, clay flats in the basins, it's not random, it's a map. A visible record of where the river flowed fast, levees, and where the water sat still, back swamps. You're literally reading the river's history and the soil types.
You can read the river's autobiography just by looking at the dirt. That is incredible.
Yeah.
Okay, this has been an amazing journey through deep time and powerful forces. Let's pull it all back together. Recap this stark contrast, this dichotomy between the coastal plain and the delta.
Right. The key thing to remember is they're just fundamentally different stories happening right next to each other. You've got the Gulf coastal plain, ancient, stable, a relic seafloor, subjected to millions of years of intense chemical weathering, lateritization. It's red clays, residual soil, the leftover stuff after chemical subtraction. Its story is deep time, chemistry, stability.
Okay, ancient and weathered.
Then the Mississippi alluvial plain, geologically young, dynamic, and active floodplain built by a huge river system. Its soils, transport materials, imported from all over North America, sorted by water energy. Its story is recent history, physics, dynamism, two totally different geological worlds.
Which brings us right back to Kay Brad's core question. Why, just that quick, why is the boundary so abrupt, not gradual?
And that abruptness is really the punchline of their relationship. Think about it. The Mississippi River system is actively depositing sediment, building the new low-lying delta right up against the eroded edge of the older, higher, stable coastal plain. The rivers are filling in that big basin, the Mississippi embayment, the boundary Kay Brad sees. It's basically the edge of the basin being filled.
So it's like pouring wet concrete,
Mm-hmm.
the delta, right up against an existing older wall, the coastal plain. There's no gentle slope between them because one is actively being built against the other.
That's a great analogy. There's no gradual blending because they weren't formed by processes that slowly merged. They were formed by totally different forces at totally different times, and they just happened to meet right here, right now. Geologically, that boundary is a profound unconformity. It's a break in time, a break in process, made visible right there on the surface. It's inherently sharp because it's where the brand new meets the very old.
A collision of geological epochs made visible. Okay, that nails why it feels so sudden. So let's just quickly tick off those key differences again, side by side.
Okay, quick summary. Age of surface. Coastal plain ancient parent materials, up to 135 million years old. Soils weathered for millions of years. Delta, super recent surface, less than 12,000 years, burying older quaternary fill.
Formation process. Coastal plain Marinda delta deposits plus massive chemical weathering, lateritization. Delta river deposition, alluviation, driven by ice age cycles.
Modern state. Coastal plain stable, mostly eroding upland. Delta active depositional floodplain, though we've managed it a lot.
Material origin. Coastal plain local stuff from the ancient Gulf sediments. Delta transported stuff ground up by glaciers across North America.
Surface deposits. Coastal plain gravels from bedrock and old terraces, residual red clay. Delta absolutely no native rock or gravel on the surface, it's all buried deep.
Yeah, and soil types. Coastal plains, those iron aluminum-rich lateritic soils. Oxisols, ultisols, delta alluvial soils sorted by the river. Sandy loams on the levees. Buckshot clays, vertisols in the back swamps. Two totally different soil worlds. Hashtag outro. Okay, Brad, we really hope this deep dive helped you figure out the thing. Your observation, seemingly simple, just opened this incredible door into millions of years of Earth history.
It really did. It shows how much story is locked up in the landscape right under our feet, doesn't it? That quick transition isn't just geography. It's a visible break between geological chapters.
Next time you're driving in Arkansas, or anywhere really, and you cross that line between the coastal plain and the delta, maybe just take a second. Think about the immense power. Oceans, ice sheets, colossal rivers, all converging over unimaginable timescales to create what you're seeing right there.
Absolutely. And that brings us to our final thought for you and for all our listeners. K. Brad noticed this contrast. What other seemingly simple things do you notice in your world, in your backyard, on your commute? What deep, ancient, maybe utterly fascinating stories might they be hiding?
Keep looking, keep wondering, keep asking those questions. Thanks for joining us on The Deep Dive.